What is a black hole? It conjures up images of emptiness, of something that sucks in everything around it. Black holes are regions in space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the very fabric of our universe is stretched to its limit, where the rules of physics as we know them start to break down. For centuries, black holes were merely theoretical constructs, mathematical curiosities predicted by Einstein's theory of general relativity. But today, thanks to incredible advancements in astronomy, we have evidence that black holes are not just real, but they're more common than we ever imagined. So how do these cosmic monsters form? What happens when something falls into a black hole? Buckle up, space cadets, because we're about to embark on a journey to the edge of everything we know. The story of a black hole begins with the death of a star, but not just any star. We're talking about stars far more massive than our own sun, behemoths that burn bright and fast. Imagine a star, say, 10 times the mass of our sun. It's a cosmic furnace, fusing hydrogen into helium in its core, releasing an incredible amount of energy in the process. This outward pressure from the nuclear fusion battles against the inward pull of the star's own gravity. But even the most massive stars eventually exhaust their nuclear fuel. The core collapses in on itself, and in a spectacular supernova explosion, the outer layers of the star are blasted off into space. What's left behind is a core so dense, so gravitationally powerful, that it warps the fabric of space-time around it, creating a black hole. Imagine a star, much bigger than our sun, collapsing under its own weight. The collapse is unstoppable, like a runaway train with broken brakes. As the star shrinks, its gravity becomes more and more intense. Think of a trampoline. If you place a bowling ball in the center, it creates a dip. That's what massive objects do to space-time. Now, imagine squeezing that bowling ball into something much smaller, like a marble. The dip becomes steeper, right? That's what's happening as the star's core collapses. Eventually, the gravity becomes so strong that nothing, not even light, can escape. This point of no return, this boundary of inescapable gravity, is called the event horizon. And at the very center of the black hole, hidden behind this event horizon, lies something even stranger, a point of infinite density called the Singularity. But we'll get to that later. The event horizon is not a physical barrier like the surface of a planet. It's simply a point of no return. Cross it and you're not coming back. Imagine shining a flashlight towards the event horizon. As the light gets closer, the black hole's gravity starts to pull on it, stretching the light waves out like pulling taffy. The light loses energy, shifting towards the red end of the spectrum, a phenomenon known as gravitational redshift. At the event horizon itself, the light is stretched infinitely, its energy completely drained. It's as if the light never existed in the first place. Anything that crosses the event horizon, whether it's a spaceship, a planet, or even information itself, is lost forever to the outside universe. So, what happens inside the event horizon? We can't send probes in to find out, and nothing can come back out to tell the tale. Black holes often get a bad rap, portrayed as cosmic vacuum cleaners, but that's not really accurate. They don't roam the universe hunting for stars. Think of a black hole like a really massive star. It has a gravitational pull, just like any other object. If you replace our sun with a black hole of the same mass, Earth would continue to orbit it. We wouldn't be sucked in. We've talked about the event horizon, the point of no return. But what lies beyond this cosmic curtain? What happens to all the matter and energy that falls into a black hole? Remember the singularity we mentioned earlier? That's the heart of a black hole, a point of infinite density where all the black hole's mass is concentrated. Imagine squeezing all the matter in the sun, or even a galaxy, into a single point. At the singularity, the laws of physics, as we know them, cease to apply. Space and time become infinitely warped. Now imagine you're an intrepid space traveler who's just crossed the event horizon. As you fall towards the singularity, the black hole's gravity pulls more strongly on your feet than your head. This difference in gravitational pull stretches you out, a process we call, you guessed it, spaghettification. But it's not just your body that gets stretched. Time itself gets warped near a black hole. Remember Einstein's theory of relativity? One of its mind-bending implications is that gravity affects time. Think of it this way. Time flows slower in stronger gravitational fields. Now imagine the extreme gravity of a black hole. As you fall deeper into the black hole, time slows down for you relative to someone observing from a safe distance. From their perspective, you would appear to slow down, your image becoming redder and fainter as the light struggles to escape the black hole's grasp. And here's the kicker. From your perspective, time would seem to flow normally. So, we've journeyed to the singularity, where space and time, as we know them, break down. But black holes aren't just cosmic sinkholes where matter and energy vanish without a trace. They can also be surprisingly loud. As matter falls into a black hole, it gets superheated and forms a swirling disk of gas and dust called an accretion disk. This disk can be incredibly bright, outshining entire galaxies, and it can also emit powerful jets of energy and radiation that blast across thousands of light years. These jets are like cosmic beacons, signaling the presence of these hidden giants. We often think of black holes as agents of destruction, devouring anything that strays too close. And while their gravitational pull is undeniably powerful, black holes also play a surprisingly creative role in the universe. Imagine a vast cloud of gas and dust, the birthplace of stars. Hidden within this cosmic nursery, a black hole lurks. Its gravity draws in the surrounding material, pulling it into a swirling disk. As more and more material falls towards the black hole, the disk heats up, glowing brightly across vast distances. This process, known as accretion, releases enormous amounts of energy, often in the form of powerful jets that blast outwards from the black hole's poles. Black holes are rarely loners. In fact, most galaxies, including our own Milky Way, are thought to harbor supermassive black holes at their centers. These gravitational behemoths, millions or even billions of times the mass of our sun, wield immense influence over their galactic neighborhood. Stars don't just sit still in a galaxy. They orbit the galactic center, much like planets will orbit a star. The black hole's gravity can send stars on wild elliptical orbits, fling some out of the galaxy entirely, while pulling others into a deadly dance of doom. This interplay between black holes and their surroundings helps to shape the evolution of galaxies, influencing their size, shape, and even their ability to form new stars. As we delve deeper into the mysteries of black holes, we uncover more questions than answers. What happens inside a black hole? Do they lead to other universes, other dimensions? Can we harness their energy? These are questions that continue to tantalize scientists and ignite our imaginations. Black holes represent the ultimate frontier of our knowledge, a realm where the laws of physics as we understand them break down. But even as we grapple with these profound questions, one thing is clear. Black holes are not merely cosmic oddities, they're fundamental components of our universe, shaping its evolution and challenging our understanding of space, time, and gravity itself. The study of black holes is a journey into the unknown, a testament to the power of human curiosity and our relentless pursuit of knowledge. Black holes, with their immense gravity and enigmatic singularities, remain some of the most perplexing objects in the cosmos. We've learned a great deal about their formation and their effects on their surroundings, but there's still so much we don't know. For instance, what's in Britain? Tatu information that falls into a black hole. According to classical physics, information should be destroyed. But this contradicts the principles of quantum mechanics. This conundrum, known as the information paradox, has puzzled physicists for decades. Then there's the question of the singularity itself. Is it truly a point of infinite density, as our current theories suggest? Or does our understanding of physics break down at such extreme scales? Some theories propose that singularities might be gateways to other universes or dimensions, but these ideas remain highly speculative. For a long time, black holes were thought to be inescapable cosmic traps, their immense gravity swallowing everything that dared to venture too close. But in the 1970s, physicist Stephen Hawking revolutionized our understanding of these enigmatic objects. Hawking showed that black holes aren't entirely black after all. Due to quantum mechanical effects near the event horizon, they actually emit a faint radiation, now known as Hawking radiation. This radiation, incredibly weak but theoretically measurable, carries away energy from the black hole. This discovery has profound implications. It means that black holes aren't eternal. They slowly evaporate over time, losing mass and eventually disappearing altogether. The study of black holes is a rapidly evolving field, driven by technological advancements and groundbreaking discoveries. New telescopes and observational techniques are providing us with unprecedented views of these enigmatic objects, revealing their secrets in ever greater detail. One of the most exciting developments in recent years has been the direct imaging of black hole shadows. In 2019, the Event Horizon Telescope, a global network of radio telescopes, captured the first ever image of a supermassive black hole shadow, confirming decades of theoretical predictions. This groundbreaking achievement marked a new era in black hole science, allowing us to study these objects in ways that were previously unimaginable. Future observations with even more powerful telescopes promise to further refine our understanding of black hole properties, such as their spin and mass. As we gaze up at the night sky, sprinkled with the light of distant stars, it's humbling to realize that hidden among them are these cosmic dancers, these enigmatic objects that warp space and time. Black holes, once science fiction, are now integral to our understanding of the cosmos. They remind us that the universe is a place of incredible beauty and profound mystery. The study of black holes is a testament to human curiosity and our desire to explore the unknown. So, the next time you look up at the night sky, let your gaze linger on the darkness between the stars, for it's in that darkness, in those seemingly empty spaces, that some of the universe's most fascinating secrets reside. black holes, with their enigmatic nature and mind-bending properties, invite us to explore the boundaries of our knowledge. The study of black holes is not merely an academic pursuit, it's a journey of discovery that has the power to transform our understanding of the universe. It's a journey that reminds us that we are part of something much larger than ourselves. The universe is full of wonders, waiting to be discovered. All we have to do is look up and ask the right questions. And as we continue to explore the cosmos, one thing is certain: the universe will never cease to amaze us.